Assalamualaikum and good day everyone. Okay, we're going to discuss about chapter 3, which is about gates and Boolean algebra. Okay, in here you will learn about logic gates, you will learn about the logic expression, you will learn about the symbol of the logic gate, and also you will learn about the truth table. Okay, in the truth table you shall have a combination of inputs and you will have the corresponding output. Okay, logic gates are primitive or fundamental building blocks for all digital circuits. Okay, so it can be described by Boolean algebra, okay, which we will learn throughout the lectures later on. Okay, we will have logic circuits. We will be using only two values, which is 0 or 1. Okay, so there is various logic gate, okay, such as AND gate, OR gate, NOT gate, NAND gate, NAND gate, NOR gate, XOR gate, XNOR gate. Okay, we will learn them one by one. Okay, okay, the concept, okay, the generic two input logic gates, okay, actually started initially from, let's say for this, for example, you have A and you have B and you have your F. Okay, F is your output and AB can be your input. Okay, each gate should have at least one input, at least, okay, one input and at least one output. Okay, so the output depends on the function of the gate and the combination of all the inputs. So here you can have your AND or NOT, NAND, NOR, XOR or XNOR gate. Okay, so let me go for the first one. Okay, we go for the AND gate. Okay, AND gate. As we learned previously in our binary multiplications, okay, when everything is 1, then you will have 1 as your product of multiplication. But if you at least have 1 0, then all of your multiplication will result in 0. So this concept multiplication is actually being used in AND gate. Okay, so AND gate, it can have 1, 2 or more input, let's say 3, 4. Okay, you can have a lot of inputs. So let's say for example you can have A, B, C and D. Okay, and then you have your output. For example, this is your Z, okay, as your output. Okay, for example, if we only have two inputs, so it can be A dot B. Okay, A multiplied by B. But if you have more input, for example this one, you can have A times B times C times D. Okay, this is your AND gate. So the logic expression is that Z equals to X times Y multiplication, or it can be also Z X dot Y. Okay, so the logic operation is that output is 1 when all input is 1. And the other logic operation is that output is 0 when at least, okay, when at least one input is 0. Okay, so what is the truth table? Okay, the truth table. So sorry, this is the general formula. Okay, if you tailor to this condition, it can be z equals to a b or z equals to a dot b if it's two input. But if, like, let's say you have more input, for example, you can have a b c d, z equals to a dot b dot c dot d, just like this. Okay, so but for simplicity, let's say we take two input. Okay, so in the truth table you should have input and you should have one output. Okay, so for example, in the case of only two, okay, in the case of two inputs, you can have a b, then you carry out 0 0 0 1 1 0 1 1. Okay, so this will be your z is as your output. So 0 0 will result in 0, 0 times 1 will result in 0, 1 times 0 is 0, and 1 times 1 is 1. Why I'm using times? Because it is actually AND gate perform logic multiplication. Okay, okay, let's say you have more input. Okay, you can actually increase. Okay, increase if you have more inputs for this case. Okay, z output, then you have this as your output, this as your input. Okay, this is your n truth table. Okay, truth table. So you have a combination from 0 0 0 until 0 1 1 1 1. Okay, remember, it give only output 1 when all of the input is 1. Okay, so we finish with AND gate. Another thing, okay, that, sorry, I forget, another thing is actually the timing diagram. Timing is diagram showing in time variation the inputs and also the corresponding output. Okay, so for simplicity, okay, we just take two input of AND gate, then you have the z and you have x dot y. So this is your AND gate. Okay, so let's say you have input of x and y, and you have your x dot y, which is your z. Okay, this is actually your n. Okay, and output. So for example, if you have 0 0 0 1, okay, for example, if you have 0 0 1, and if you have 0 1 0, okay, so 0 0 you get 0, right? 0 1 you will get 0, 1 0 you will get 0. But let's say if we increase this one to 1 and we increase this one to 1, then 1 times 1 you get 1. So your timing diagram will be look like this. Okay, so this is your timing diagram. AND gate, timing diagram. Okay, next we go to the lock gate. Next we go to the OR gate. Okay, so from the word OR you can know actually at least, okay, because it's OR, right? One at least one input, then you will have output of 1. Okay, so the similar with AND gate, it can have more than one input, but it will have one output. Okay, for example, for simplicity, this is the OR gate. Okay, so you have your X, you have your Y. Okay, this one is not fixed. You can use A, B, C, D, and so on. Then this is your Z as your output. Then you have X plus Y. Okay, so this is actually showing the operation. Okay, so you can have more. Okay, let's say X, Y, you can have Z. Okay, so don't rigid yourself. And then, so what is the logic expression? Is actually Z equals to X plus Y. Okay, so what is the logic operation? What is the logic operation? It is that output is 1 when at least one input is 1. Okay, the other one is output is 0 when both or all. Okay, this one is for the case of 2 input or all. This one is case if you have more than 2 input. All input are is 0. Okay, the same as well. Okay, understand? Here mentioned that output is 1 when at least one input is 1, and output is 0 when both for 2 input or for 2 input condition, or all input for more than 2 input is 0. Okay, so we can see the truth table. Okay, so we can, let's say for example, if we want to use okay, your truth table should have input and output. For example, if I want just to use this case, okay, X, Y, and Z is 3 input. Okay, for example, then have this as your output. So output is 1 when at least one input is 1. Okay, for example, in this case, okay, you can have 0, 0 combination, 0, 0, 1, 0, 1, 0 until 1, 1, 1. Okay, so here output is 0. Okay, when both or all input is 0. This one satisfies this, so this is 0. How about this one? We have at least one input as 1, so the output is 1. The same goes for this, and the same goes for this. Okay, try to fill up the truth table yourself. If you have problem, you can always approach me. Okay, how about the timing diagram then? The timing diagram, okay, for simplicity, I just used 2. You can have more than 3 or 4 or 5 inputs, right? But so for simplicity, okay, timing diagram the same for this. Okay, but we reduce it only to 2 input. Okay, so if you have a timing diagram, let's say this is your X, this is your Y. Okay, okay, and then 0, 0, 1. This one you have 0, 1, 0. Okay, and what is your Z? What is your Z? Okay, so you know Z is actually X plus Y, right? Okay, you know that your Z is X plus Y, and this is for the OR operation. Okay, so 0, 0, because all is 0, so you should have your output as 0. This one, at least one input is 1, so you have 1 already. and the same here, at least one input is 1, so you continue to have 1. Okay, so far so good. Next, we go to the gate that we call as NOT gate. NOT gate, also known as inverter gate. Why? Because it simply invert the input. Okay, let's say if you have input 1, then you have your output 0. If your input 0, you have output 1. Okay, so NOT gate only have one input and one output. Okay, only have one input and one output. Okay, so perform logic inversion. Okay, it perform logic inversion. So the logic expression is Z equals to X bar or Z equals to X prime. Okay, while the logic operation is output Z is opposite of input X. So what is the symbol then? You have your X as your input and you have the NOT gate. Okay, so output is X bar. This bubble actually indicates inversion. So how about truth table then? It's simple because it's just inversion. So if input is 0, then output is 1. If input is 1, output is 0. Okay. So how about the timing diagram? The timing diagram is quite straightforward. Okay, simple that you have X as your only input, then you have, let's say for example 0 0, then you have 1. Okay, then your Z, which is the NOT. Okay, your output is a inversion of your input, which in this case is X. So 0 you will have 1, this one you have 1, this one you have 0. Okay, simple. If anyone have problem, you guys can tell me. And just for everyone good to know, can anyone guess what is, okay, good to know, what is this? Then if this is NOT gate, and what is this? And what is the output? And why do we need this in digital circuits? Okay, so as I mentioned to you guys, for logic gates we can have more inputs. Okay, so you can have 2, 3, 4 or 5 inputs. It's not limited to only 2 input. Okay, for example, if you have more input of AND gate, you can have more, right? If you, how about OR gate? If you have more input, you can have more input. For example, okay, you can have more A, B, C, D, E, and let's say you have your F or Z, whatever, if your output. So for example, the OR, you can have F equals to A plus B plus C plus D plus E. Okay, next we go to the other gate, which is the NAND gate. as the name implies, means there is an element of n and there is element of n here. Okay, this one is actually AND gate. This one is actually your NOT gate. So in this condition is actually the input passing through the AND first and then will passing through NOT after that. Means whatever output that you obtain from your AND gate will be inverted because it will pass through the NOT. Okay, it is a universal gate. Is used to perform AND or and NOT operation. Okay, for here, like I told you, it will go through AND first and after that it will be NOT. So first is your AND gate, after that it will undergo inversion. So you have okay. So this is in the previous slide, in the previous lecture is mentioned as inversion, right? So this is your x, this is your y, and this is your z. Okay, so the logic expression is actually z equals to x dot y and invert. Okay, you may also write as z equals to xy invert. So what is the logic operation? Output is 1 when at least one input is 0. Okay, the next condition is output is 0 when all input is 1. So it is simple. Okay, the NAND truth table this is your output and this is your input and this is your x and y, this is your z as your output. Okay, so we do, for simplicity, we use 2-bit two inputs. Okay, so how we fill it fast? Okay, like for example this 0 0 for AND gate, 0 times 0 0 and invert that, then you get 1. 0 times 1 you get 0, right? After that you invert it, you get 1. 1 times 0 you get 0 also, and you invert again it because it's here. First you multiply, then you invert. Okay, 1 times 0, 1 multiply 0 0, then invert, you get 1. 1 times 1 1, but you invert, then become 0. Okay, here output is 0 when all input is 1. So you can try out yourself for many input. For example, if you have z, if you have more input, okay, you can try yourself. So NAND gate is universal gate. Okay, you can see from the slide, 13 or 34. Okay, I will share this slide and you can refer, and you also can refer for further information at the module. Okay, so NAND is a universal gate. Okay, is universal gate. Okay, one of it can use to produce NOT gate, your AND gate, your OR gate. Okay, for example, to have OR gate with 2 inputs. Okay, 2 input x, 2 to input x, y. Okay, so what can you have? Okay, you can use NAND gate, 3 NAND gate to produce an OR gate. Okay, for example, okay, what is the condition? We take, we see from the example for the, okay, let's see, for OR gate, 1, 0, for example, 1, 0, you will have 1, right? Because it's, for example, this one, let's say x, y, z, here is z equals to x plus y, okay? So at least one input is 1, then you will have one output, okay? So here, for example, you can use 3 NAND gate to produce an OR gate. For example, if you have 1 here, okay, for example, you have 1 here and you have 0 here. It's the same, okay? 1, 0. 1 passing through here, okay? Then you have 1 times 1, you get 1, right? They go through here, but then you invert, then you have 0 here, okay? How about here? 0 times 0, you have 0. However, when you invert, you will have 1, okay? Then you have carry on to here, okay? 0 times 0, you get 0. However, then you invert it with 1, then you have 1, okay? So you can see the input is the same and the output is also the same. Okay, you can try for the other circuits, for the other combination, test yourself. Next, we go to the next slide, which is the NOR gate. Like NAND gate, it also means that this is your OR gate and it is your inversion gate. Okay, mean it will pass through OR gate first, then it will pass the inversion. It's also a universal gate. It is a contradiction of not OR, okay? Means it will pass through, for example, the same, it will pass through OR gate first, okay, OR gate, and after that it will pass through the NOT gate. So what is the logic expression? Yes, it is z equals to x plus y inversion. X plus 1 for all, then inversion, okay? So logic operation is that output is 1 when all input 0. The next logic operation is output is 0 when at least one input is 1. Then the same for the truth table, for example, x, y, and z as your output. You can try yourself if you want to use, you try with, let's say, a, okay, as the other input, okay? You can try. Don't limit yourself. You can do self-experiment. But for simplicity, for self-understanding, I will, and for fast, we don't take much time, I will use only 2 input because the concept is just the same. So for x input, you have 0, 0, the same, 0, 1, 1, 0, 1, 1, okay? This one you can do yourself, okay, later on. So it will pass through OR gate first, or 0, 0, or is 0, then invert, then you have 1. 0, 1, or means 1 is already, at least 1, then you have 1, but invert, then you become 0. 1, 0, or you have output 1, then you invert, you have 0. 1, 1, you have both 1, then you output at here is 1, but then you invert, it's become 0. Okay, so you can see that output is 0 when at least one of the input is 1, but you have output as 1 when all input is 0. Okay, similarly, like the NOR gate, like the NAND gate, this is also a universal gate. Okay, you can try yourself. It can be used, this NOR gate, to produce NOT gate, to produce AND gate, and to produce OR gate. Okay, okay. Similarly also, this is your NOR gate. Okay, so you can try. Okay, you can test yourself, then you will see that this and this will have the same input here, and also will have the same output. Okay, try yourself, and here you can try. If you have problem, feel free to ask me. Okay, so the next we have is, we call the exclusive OR gate. Okay, or in the short form is XOR. XOR only have two inputs. Okay, the logic expression is Z X bar Y plus X bar Y bar. Okay, or ZX exclusive or Y. Okay, this is the symbol. Okay, to denote the is this XOR. Okay, you can use either one, this one or this one. Okay, so output for this case is output is 1 when X, Y are different. The next is output is 0 when X, Y are same. Okay, output is output is 1 when X and Y are different, and output is 0 when X, Y are the same. So simple. So you have for truth table, so you have the same, you have input and you have output, you have your X, you have your Y, then you have your Z. This is the combinations of possible inputs. Okay, you see output is 1 when X or Y are different. Okay, so which one is different? This one and this one. So you have 1 and 1. The same will result in 0. Okay, so how about the symbol of logic of XOR? Okay, it's just like OR, but we have this. Okay, so this is your XOR. Okay, the operation is X XOR Y. Okay, exclusive OR gate. Now, how we going to convert, how we going to construct XOR using basic gate? Okay, how actually you produce XOR from AND or not. Okay, the logic expression, we learned that this and is equals to x y invert plus x y invert. Okay, so let we consider this. Okay, so first you have your x and y. Okay, so you imagine this is one possible input and this is one possible input. So let's say you have your x and your y. For this one, you have your x, this one is means n. Then how about this? Invert. Okay, this is your x, y. Okay, x, y bar. Then the next combination is that you have your x bar and y. So you have your y and you have your x. Okay, but invert. So you have your not. Okay, and what is the third, another last operation? Then you have your plus here. Plus means it's or. Okay, so here so this or is actually means addition, right? So here, so the output is x dot y invert plus x y. So simple, right? You can try yourself at home. Next, we go to the next concept, which we call it exclusive NOR get. Okay, what is the short term of that? X NOR. Okay, so it has only two inputs and the logic expression is z equals to x, okay, y plus xy bar like this, or you can have z x exclusive or y, then invert them. So it is simple. This is what your x or, then you simply invert it. Okay, whatever you have produced from here, then you invert it as your final output. Okay, so this one is the more compact form. Okay, this one will help you to understand what is actually happening. So for the logic operation, z output is 1 when input same. Okay, when the input are same, and you have output 0 when input different. Okay, so it's actually inversion of XOR. Okay, inversion of XOR. So you have your input and you have your output, the same truth table. So you have your x, y, then you have your z, 0, 0, 0, 1, 1, 0, 1, 1. Okay, it is actually in the vice versa of XOR. So if your output is 1 when your input are the same, and your output is 0 when your input are different. You see where is you have the same input, you have here and also here, right? So that's why this will result in having output of 1. When your input is different, this one, the combination are different, then you have it as 0. So what is the logic symbol then? X is your input, and you have your X, and you have an element of OR. Okay, and I told you it's inversion of the XOR gate, inversion of XOR gate. So you have your OR as the basic one, then you have XOR, then you have inversion here. Okay, so this is your inversion. So Z equals to X exclusive OR. Okay, this one is actually XOR, but to have XNOR, so ZX inversion of this. So this is your XNOR. So far so good. So now we go to how to make XNOR using combination of AND, OR, and NOT. Okay, so you go back from the equation, from the expression, you further elaborate it. Okay, just like XOR. Okay, try yourself. Okay, try yourself with using these combinations. How you going to have the Z? Okay, okay, try first. Okay, it's just the same as XOR, almost the same, but you need to alter a bit because in the end you have inversion. So I want to ask you what is the timing diagram then, corresponding timing diagram. For example, okay, if you have here and you have another one, for example, this is what? This is your XOR, okay? So we may have a variation of input and variation of input that will result in corresponding output. So I want to try you guys to just test, okay, test yourself at slide 20 of 34, okay, from the presentation slide. Try yourself and try to understand. Okay, if you have problem, you can always feel free to approach me. Okay, try to understand the timing diagram and maybe to test yourself. Okay. Okay, we will finish that in the next lecture. Okay, we will continue with Boolean theorem, Boolean algebra, which is the addition, multiplication. We will study about laws of Boolean algebra, which is commutative, associative, distributive. Okay, and finally we will learn about De Morgan's theorem. Okay, so see you guys and good day.